Welcome, we are from team Force Racing and today we will be studying about tyre behavior. In this, one thing we notice that the power we supply or the downforce which the aerodynamic produces is going through 4 small contact patches on the tyres. Now let us start with coefficient of friction. In this, F is the frictional force, mu is the coefficient of friction, N is the normal load. In this graph, as we can see, if we increase the force, then the coefficient of friction increases and it dips. At this point is known as static friction, and then it dips and becomes constant. Now let us go to the lateral force. The force that is produced sideways due to the deflection or compression of the tyre is known as the lateral force. While we corner, there is a cornering force that is actually the lateral force. This lateral force is generated by the slip angle, which we'll study next. Contact patch. The area of the tyre that touches the ground is known as the contact patch. The whole tyre doesn't touch the ground, so there is a small area which touches the ground, which is known as the contact patch. Now we go to the most important thing in tyre behavior, that is the slip angle. The slip angle is defined as the angular displacement between the plane of the wheel and the path that the tyre will follow on the road. Now if we rotate our steering wheel about 5 degrees, then our tyre rotates only about 3 degrees. This difference in the angular displacement is known as slip angle. Now let us consider a point on the contact patch. We assume that the car is moving and cornering as well. Here we take this point, and due to its longitudinal movement, that is the aft movement, the point keeps moving down, but due to the lateral force also gets deflected sideways. Here at this point the deflection is max and then it starts to decrease. That is because the vertical load at this point starts to decrease, so the frictional force decreases, and at the trailing edge it just comes back to its normal position. One thing we notice is that if this is considered to be the midpoint, the lateral force is at the rear of the contact patch, so there will be a torque at this way. This helps the tyre to come back to its original position. One of the most important graphs in slip angle is this lateral force. For tyre behavior, this is one of the most important things we should notice. Here we see for a particular slip angle, we have a particular peak load. This peak load is what we need to optimize to see the tyre behavior of our tyre behavior. Now suppose we increase the range of the slip angle to give us the same peak load for a different peak load. This is used for FSAE teams because our drivers aren't well trained. So here we have a larger range of slip angle where we can get a peak load, whereas the range of slip angles is very small. Here this is used, small slip angles are used in Formula cars and for well trained Formula 1 drivers. Now one more important thing we notice in this is there are 2 points for the exact same peak load. What does this signify? This signifies that this part and this part. As we know that alpha versus F will give you energy under a graph. We see that here the energy is less, whereas here the energy is more. This energy leads to tyre temperatures. Now the tyre temperature at this slip angle is less, whereas at this, unless we have set up our car for higher slip angles so that it takes more heat, we should not use this higher slip angles. Now we will go to sidewall stiffness. Now making the sidewall stiffness softer increases drivability. That is because here this is a tyre with a normal compound and this with a softer sidewall stiffness. Now we see it produces the same peak load but at very different slip angles, this and this. Here the range is also less, whereas here the range is more. As we can see that, but one thing that Formula 1 drivers are that they drive at these slip angles, at lower slip angles. So there should be a trade-off that they are not using these slip angles because everyone can drive at 6 degree slip angle because it's easier to drive. But one thing is that if you drive at 6, the heat under the tire or the drag, not the aerodynamic drag but the drag of the tire is more, and this causes graining. So Formula 1 drivers use the smaller slip angles. Now we go to normal road. When we have slip angle versus lateral force graph, it depends also on the normal road. If we increase the load, then the peak lateral force also increases, as we can see here. But when we signify these points on these graphs, we get another graph that looks something like this. So this change in frictional force we can signify in another graph with slip angle, that first point, second point and third point, something like this. One of the important concepts is tire load sensitivity. When we see it on a microscopic level, we see that this tire surface goes into the road surface something like this when normal force is applied. When you increase the normal force, the whole tire surface gets embedded into this road surface. But when we further increase the normal load, there won't be any change. We will already attain the maximum grip. This is a concept of tire load sensitivity. If we see it in these terms, mu is equal to Fr by n. When you normalize it, that is when we divide it by load on tire, we get that lateral force by load on tire gives us a lateral force coefficient. When you plot a graph with the lateral force coefficient and slip angle, we get something like this. We might have seen this graph before, that is alpha versus lateral force graph when we change the loads. But one thing is converse in this, that the loads are in decreasing order. Slip ratio. The center of the wheel spins faster than the outside of the wheel. This is the definition of slip ratio. Slip ratios just like slip angle but in a longitudinal sense. Now slip angle. How the slip angle is for the cornering force is the same way the slip ratio is for traction capacity. One of the main misconceptions in slip ratio is that when the wheel gets locked up or when the visible wheel spin occurs, it is known as the maximum traction limit. But actually, we reach the maximum traction limit just before the wheel spin or the lockup. Now we go to the friction ellipse. In a friction ellipse, it is a graph between the force lateral force and the longitudinal force. Here we can see that these points give us the maximum lateral force and these points give us the maximum longitudinal force. There are many different set of tires for which the graph changes. Some have this kind of shape where there is this rectangular shape. Some have a total circular shape. In the rectangular shape, you can see that we have pointed ends, but there are less peak values, and we have in the circular shape you can see that we have more peak values but we don't have a pointed end. This doesn't mean which is better, it is just that it depends on the use of how we use the tire. Now we have seen the basics of the tire behavior. Thank you.